Yeah, as okay, as I said, this is just a nice excuse for me to just come to Austin and hang out with friends. But yeah, the title of this talk is Building, Evaluating, and Improving Language-Guided Robots. This is a tentative title for my thesis defense next month, but in practice, I'm only going to talk about like subsections of these to keep it shorter. Um, but I just want to put an about me slide, like Rutov said. I did my undergrad here, working with Justin and Peter, like wow, like 5 years ago now. And I was reminiscing earlier today looking at old pictures that I had. So I just wanted to put those in here, like working on RoboCup at home. Joydeep is in the corner back there of that photo that I took back in 2019. That was like his first year here at UT. Just fun stuff. And Justin, if you remember, there's like Nick Walker and Stone Tejeda during the first robotics camp. Uh, anyways,
Oh, nice.
yeah. But yeah, and then I'm working with Jesse Thomason at USC, who is also a UT alum from doing his PhD with Ray Mooney here. So a lot of Longhorns, I guess, in the whole thing. Yeah, but I'm going to be talking about. Oh, let me pull some things up. So yeah, in like I think like generally a lot of us want like robots that can like clean up very messy homes. Like if you want robots to go to these unstructured environments and have robots clean up, like, make the bed, sweep everything, and all these kinds of different tasks. But like if we want to think about how we want to design robots that can do tasks like this, we have to like think about this like systematically. So I like to call this the robot learning life cycle. So I don't know what the right term will be. Maybe we'll define it more formally later. But the first thing is you want to develop different kinds of algorithms for your robot. You, uh, it might be VLAs, it might be like more engineered systems. I'm just keeping it very vague for now. And the next thing you generally do is you evaluate the performance of your robot. And then based on those evaluation metrics, you iterate on that solution. You try to improve your robot and like come up with different ways of like having a better step change over time. So I'm going to be talking about these things through what my thesis is going to be about, which is like natural language provides structure that enables our robots to generalize across tasks, evaluate their own capabilities, and that language helps us improve during deployment. So through this, I'm going to be talking about three different works. A robot work. Oops. I'm going to be talking about it from three different works. I'm going to skip the first one, but I'll talk about how we build robots that can uh, like perform multiple kinds of tasks and focus more on how do we evaluate those robots and then how can we improve those kinds of policies. So I'm just going to let this play as I talk, give some context. So this was a project I did at NVIDIA like 2 years ago with Joydeep at NVIDIA called Remember. And the main premise of this was just like this is going to be super high level, but the main premise of this was to build robots that can like build long-term memory over time. And when you ask it to navigate to certain places, take you to different kinds of things, you ask it open world tasks, can we build a retrieval and memory system that lets us like do this kind of planning in the open world? The main premise of this for the context of this talk is that we're getting to the point where we can start having these more open world like language guided robots that can do multiple kinds of tasks. And this was like one variation, one take on how we can do something like that. And now people have been doing like VLAs or other kinds of systems to try to like build these kinds of systems. I just like showing this video because it's like the nice NVIDIA campus. Um, but yeah, like you can get it to take you to a bag of chips and other kinds of like just open world things uh, over time. But anyways, I'm going to skip through this and then talk about if we have robots that can perform multiple tasks, how do we evaluate them? Because like robotics is a very systems oriented thing. You've built these algorithms, but you need to improve it over time. You need to evaluate it and you need to come up with those overall systems. So thinking about this problem, um, like I want to first talk about how we actually evaluate robots more generally. Like generally, first we train a robot policy. I'm going to take a more learning-based approach as I talk about this. But we train a robot policy and we can train it on like whatever data we have, human videos in the wild, data, teleop, simulation, whatever. But then we usually generally evaluate it offline. And that can be through loss functions. And we generally find like intuitions like the larger policy that you have, the more data that you have better loss functions. And that should, in theory, lead to better downstream performance. But almost never does that actually correlate to downstream performance. And I think that's one of the big issues with offline evaluation. So a lot of people have then started working on evaluating in simulation, and they've been creating more and more hyper-realistic simulations. Like from Google, there's like real to sim work and all of this just to help improve this like evaluation pipeline in simulation. And then the last thing that you do, which is usually just you evaluate in the real world, and a lot of people have been working on different approaches like Robo Arena to come up with ways to do this evaluation in the real world and make it more reliable. But I think the main thing to note is when you do real world evaluation, which is like this gold standard for evaluation, it requires a lot of experimenter time and effort. And when you have multiple policies, when you have multiple tasks that are open world, hard to define, uh, how do you actually do that kind of evaluation more efficiently, especially as your goal is to iterate over time? So I think this just goes through each of these, the pros and cons for each of these. Like offline eval is easy to run, simulation's easy to run, but you can't create it in every environment. The real world is the gold standard, but it's very expensive. So this is what I'll be focusing on with the main paper that I'll be talking about. Um, Offline evaluation would be like looking at your loss functions, comparing to offline data, doing, oh my God, I forgot the name of it. What is yeah, just like offline evaluation approaches. Yeah, like usually loss functions, I guess. Um, yeah. So the main context of how I've been thinking about this problem is, let's say you have multiple different tasks, like pick up the blue mug, to pour the milk, to open the door, whatever these open world tasks can be defined as. And then let's say you have like 4 policies that you're iterating over and you want to test all these. There's going to be 5 policies, 20 policies, however many it is. Whenever you change between tasks, that incurs like a switching cost to go from one task to another task. And that can start to become expensive as you evaluate across multiple policies that you have available to you. So the way that we've been thinking about this problem is similar to a probabilistic matrix completion problem. So I'll talk about it at high level. Let's say you've only run a certain number of policies and tasks in this like matrix of policies and tasks. If you're trying to evaluate a new task, like can you come up with an estimate that is a reasonable estimate for what that policy task pair actually performs at? And that's kind of the goal of what we're trying to do here. And so this is the context of my last Coral paper. Efficient eval of multitask policies with active experiment selection. So we formulate the problem as like similar to that of like an active learning problem where the outcomes, instead of actually learning something, or learning like some kind of downstream performance, it's to learn how to test your policies. So let's say you have like the setup that I described earlier. You have a set of tasks, you have a bunch of policies, and there's like a large combination of like policy task pairs that you need to evaluate. So the way we think about, one way to think about evaluation is that it's a distribution of performance across every policy task pair. So for any given policy, you might have like if you assume you get like a continuous reward, let's say, your policy might perform very well or perform poorly, and you can represent that as a bimodal Gaussian over multiple evaluations that you do. Or if it's like you can represent it as a binomial distribution if it's like successes and failures only and not a continuous distribution. So we've been treating this as like a population parameter estimation problem. So if you can come up with a representation of your task in your policy, I'll keep that relatively high level for now, and you pass it through an MLP, what you want to learn is the distributional parameters of your of the performance of your policy at the end of the day, of a policy task pair. So that's the framework that we're leveraging here.
The policy for MLP.
So we only have, I'll talk more about it later. Okay, actually in the talk I didn't keep it in there. We've been exploring a lot of different policy representations for the actual Coral paper. The main thing, we just used a random embedding to represent like each policy on its own. So we assume no priors over like the relationship between policies. So
policy is like
it's just a one-hop embedding essentially.
It's like a word, and the policy embedding is like a token of the word.
Your policy embedding is a token of the word. Unfortunately, that's not how we do it. So like if you have like, let's say all of these policies here, like OpenVLA, Octo, RT2,
like what?
Like it's a one-hop embedding 1, 2, 3. So that's like the naive way where you assume there's no relationship between any of your policies. We spent a lot of time looking at how to create like an optimal version of this embedding where you have a priori information to like understand if a good policy, like if policies are like, let's say they perform well generally, they would be located in one region of embedding space, and if they're poorer, they'll be further away. We can like train these kinds of like we can train that given given all that information a priori. That's like not an ideal setting, so we don't really talk about it much in the actual paper. But we've been working on new ways to try to represent policy embeddings by looking at like VLA activations. But that's very early, or it hasn't been working so far. So
yeah, because for example, if I fine-tune the open VLA a bit, then it should be closer to like 0.9 or 1.1 rather than just giving it a completely new, like bigger.
Yeah. So like I think it's an like for the sake of evaluation, I think like the policy representation is like a very interesting problem. We kind of left it as like open future work for this paper here. But I don't think I'll finish it in time for the PhD, unfortunately, but I tried. But yeah, go ahead.
Why don't you just use simple like observation embedding
for observation embeddings? We wanted it to be more at the task level instead, because like we had a lot of data that have like very different instantiations of what the initial embedding is. I do think like if you use like, let's say the first observation or actually we're working on this now. If you use the first observation and you have the latent embedding from your VLA, so like pass it through your VLA's image encoder and take that embedding, that's like a combination of like that observation, the task, and like the policy itself, right? That's like a decent compact representation of what that combination looks like. We've been looking at that for like safety implications recently, but like for the sake of this paper, we didn't do that. Yeah.
You assume the policy space are kind of continuous?
Yeah, here we do assume it's continuous. So if we have like 50 policies with the optimal embedding, you can like, it's like on a like it's on a unit ball, right? All of them have like a norm of 1, and like they're just going to be different spaces away. Yeah, in terms of cosine.
A really bad policy. The middle, like your 50 policy, like number 25 is a
really bad policy.
Then just change the landscape dramatically.
Yeah. I think like when I qualitatively inspected all these embeddings, like when I used all the like data a priori, all the bad policies were located in like one region of the embedding space, and then all the good policies were like more scattered depending on what tasks that they were good at and what tasks that they were bad at. But that's something you can only do if you know the outcomes of your evaluations before you do the evaluations. So the premise of how we're structuring this is that we don't want to make assumptions about what we're going to be evaluating after the fact, right? Yeah. So like the assumptions are slightly different, but I think what you said makes a lot of sense. Yeah.
Can you just explain once again why it?
So generally you find that policies tend to perform really well or they perform poorly, right? And they're not actually very often in the middle. It's like catastrophic failures or like reasonable successes. So like when you look at rewards for like meta world, let's say, or you look at like partial progress, like partial successes and stuff like that, it's either like almost always 0 or it's like 0.7, like, and not really much in the middle. This is like true across all the evaluation data sets that I looked at. When I was trying to do like unimodal like Gaussians to assume that that's the shape of the distribution of performance across multiple kinds of tasks, it just doesn't work. And I made this like one simple change and suddenly everything just like worked. Go ahead.
For the tasks that you looked at, are they mostly short horizon tasks in which like you either succeed or fail by basically so much?
Yeah, they're all like, yeah, all of them are generally like simpler manipulation tasks. Like in simulation, we did take evaluations from other people's papers. So we got the evals from OpenVLA and Hamster, like 2 different VLA papers where they have this is the next slide after this, but like we took their evaluations and then we constructed our problem formulation of active learning with the data sets of evals that they had already done, and we like simulated them offline. And those were longer horizon, so we found the same kind of premise holds with the bimetal Gaussian. So that was interesting.
So if there's only 50 policies, why didn't you just hot encode them all?
Hot encode all the policies.
Just each policy is a different one hot vector.
Oh, we did.
Oh, that's exactly.
Yeah. So those are the two cases. You can have like an optimal version of this embedding. So like you train the embedding space to like look like how you think it should look like, or you can just have them be like a one hot encoding.
Okay.
Yeah, those are the 2 situations for how the policy embedding looks like. The task embedding is like a language embedding. So like keeping it relatively simple.
The policy, the one up, you expect, if you know the performance of 49 policies on one task, you expect that information to help you on the next policy.
It does not, right? Yeah. But you can find it for, yeah, you in theory can do that. So when we did this, like when we have this like optimal embedding a priori, you like where you train on all this data a priori, that like you find those clusters actually do help you. There is some transfer. It's actually not as much as we thought, which is why we created this optimal embedding kind of structure. The more interesting thing that helps a lot is the language embedding, because that represents like the task itself that you can learn through your MLP. So you can generally learn the structure of like, if this one task is hard, it's probably hard for every policy generally. And that's like a nice intuition to have. Like, I guess I should have started with this. Like if you pick up like a coffee mug, right? Like that's very semantically similar to like picking up like almost any other rigid body object, like a water bottle. So generally there's like good performance between these two policies, task pairs. So we can find like if you can do well on one task, you have a good prior for what the other task will look like before you even do any evaluations. There's this like task-wide generalization that you find. Yeah. Yeah. So basically the goal of our surrogate model is to learn these like distribution performance parameters. And once we have them, we want to use this to figure out what kind of experiment we want to sample next. So we do this by scoring all the prospective experiments that we have. If you recall the matrix that we had, we want to score what the estimated performance on every single one of these are. So the first thing that we do is we take our MLP, our surrogate model, and we perform Monte Carlo dropout to sample multiple of these distributions. So essentially we drop out different weights of the MLP so that we get more variation in terms of the distributions that are output. So for example, like let's say put the eggplant in a pot, when you do multiple Monte Carlo samples of forward inferences, you might find that all the distributions look the same when you sampled like 5, 10 distributions. So this means that it's like implied that if you try to sample another, like if you grab a new sample for this data point, you won't actually learn anything new because like these distributions are like pretty well set in terms of what your surrogate model had already learned. And we encode this as expected information gain. And I'll talk more about what expected information gain metric we use. We use like a Bayesian active learning by disagreement approach over these like probabilistic distributions. But the intuition is that the more disagreement there is between the sample distributions, the more likely if you sample another experiment for this policy task pair, you're going to learn more information about like what the structure of your policy task pairs look like. And so we can compute this kind of expected information gain across all policy task pairs, and running every single like task, like switching between tasks will also incur like a cost for running every experiment or like switching from one task to another. And you can assume a landscape of like switching costs in terms of how you do evaluations. So we can have like these two as our like inputs essentially. And we can design acquisition functions based on these. And I'll talk more about which acquisition functions we use in like a later slide. And once we do that, we can sample what the most informative experiment is going to be for that cost. And then we can run that experiment, add that outcome to our data set, and we can retrain our surrogate model. And we keep doing this in an active learning fashion over and over again. So like, that's like the structure of like everything essentially. Does that make sense? Cool.
What I'm confused about is you said that the cost of the experiments also depends on what experiment you ran prior, right?
Yes.
So is this like basic cost function something that you have to define manually, or?
For this, yeah, we did define it manually.
I see.
Yeah.
And so like,
Or in terms of like let's say like you're switching robots for like doing an evaluation on one robot versus another robot. There's a larger switching cost for like switching between what evaluation you're doing on different robots. Or let's say one task happens in a kitchen and the other one happens in like the living room, right? There's like a larger switching cost to go from like one room to another. Like these kinds of switching costs are what we encode manually.
And how sensitive is this like approach to basically setting like an appropriate relative like switching cost? Like how much tuning did you have to do?
I didn't do any tuning actually. So like I'm sure the results could actually be a lot better. I did like a little bit of tuning, but nothing like it just like an hour or two, and I was like, this looks good.
Okay.
Yeah. But all of that is like all of those like all that tuning is like after the fact about the scale at which your costs are not based it's not based on like and so I just had like a simple like parameter to weigh it better with respect to the expected information gain metrics.
So it seems like you would need quite a lot of iterations of this to get from a randomly initialized SLP to something that actually knows anything.
Yeah. So
So how much sampling did you have to do?
before
How
it got
big was your
reasonable, yeah.
model and how did you train it?
It was like a very small MLP. Like there's just like a 3-layer MLP or 4-layer MLP. And it takes about like it depends on the data set, but it takes about like 200 evals before you start getting something reasonable, 300 evals. And this is like one eval each across every single one of these. But to on your point on like having reasonable performance, there's like this cold start problem that happens in a lot of active learning literature, where when you start initially, all your acquisition functions are like useless because like you have no priors, like all your sampling is just going to be random, right? So to mitigate that, we initialize, I think, yeah, we initialize, okay, I'm going to talk about the next slide. I'm going to show a visualization. I'll tell you what we initialize with. Remind me about the question if I forget. But over this data, we sample over, look, we take 3 different data sets. We took Hamster, which has 81 tasks, 5 policies, and they measure a continuous task progress metric. We take OpenVLA's evaluations, which have multiple embodiments, multiple tasks, different policies, and they only look at success rate as the metric. And then we create a bunch of different variations in MetaWorld for evaluating multiple tasks and policies with continuous and discrete types of evaluations. And so I think this is a more intuitive result to look at. It's a little hard to look at. So on this right-hand side is the true distribution for policy performance. So like each one of these is the darker the color, that means the higher your performance is going to be for a specific policy task pair, assuming you ran every single evaluation that you have in your data set. And so this is like the evaluation, like performance distributions overall, if you take the mean performance, right? So when you initially start, like it's useless, right? Like there's no prior information at all, so it's always really bad. So after the very first step, what we do is we evaluate 2 random tasks. So it's policies as rows and then tasks on columns. So we take we took 3 different tasks that we just randomly sampled that are very diverse in task space. So we take the language embeddings and we find that just like 2 or 3 very diverse different tasks, and we evaluate them in full across every policy task pair. So that gives like an initial prior for how good every policy is across a bunch of different tasks. And then it gives you a good insight on which types of tasks are probably harder or easier. So that's what we do to mitigate this problem. But as you can imagine, as we do more and more evaluations, like 150 evals, 750 evals, like intuitively here, you can see that the distributions initially look very different from like the true distribution that it should try to approximate. But over time, as you do like 750 evals, it's very close in terms of approximating that true, like the true performance distribution. And the thing is 750 evals is like it's like 1/3 of all the actual evaluations you need to like get that full distribution that you see on the right-hand corner. And the insight should be that as you do different policy task evaluations, because there's like shared information between different tasks, instead of doing like 20 evals for a specific policy task pair, perhaps if you have multiple policies and tasks that you do evaluations on similar related tasks, you get a decent enough approximation of a task that you did like fewer evaluations on. This is a very intuitive thing I'm just describing here. Go ahead.
That's 1 and 0 mean. Is 1 like with performance and 0 is very bad?
Yeah.
Oh, and what does each row and column?
Yeah. So the rows here are the different different policies and the columns are very different tasks. So for example, you see this like very white one. So that's a very bad performing policy. And then the much darker ones are like better performing policies generally. So it is interesting to see like over time, like policies that perform well, like are generally darker across all tasks, even though it might not be true early on, but generally like the MLP starts to learn over time, like, okay, this policy tends to be really good, this policy tends to be really bad, and it'll have that implicit structure beforehand. And so that saves you on a lot of evaluation that you may or may not need to do.
And Meta Hamster, and OpenVLA, are they the names of the policy? Or
Oh, those are the names of
the
the benchmarks where we pulled evaluations from.
With the X, so the y-axis is the policy, right?
Yeah, there's like 1, 2, 3, 4 OpenVLA policies, and that's what you see here that they evaluated on. Yeah, I asked Carl for giving me the OpenVLA evaluations that they had, so that's how we did a lot of these offline. Yeah. Yeah, so this is like the insight. So like the metrics that I'll show in later slides are essentially like these are the estimated means across for every policy task pair. So in the later slides, I'll be showing what the L1 error is for the means that are predicted versus the true means that there are. There's other metrics in the paper, but I think it's easier to talk about like the error of the mean of each of these distributions as opposed to other like distributional metrics.
So let's
Yeah, go
question
ahead.
about the initialization.
Mhm.
So you mentioned you random sample 3 tasks.
Yeah.
Policies.
Or no, 3 tasks, all policies.
All policies.
Yeah.
I see. How sensitive is the evaluation evolved with
With the initial
Yeah.
starting. Yeah, we did a bunch of different, so like in this for this, we only did like 1 run, but for like all the metrics I'll show in later slides, we have different random initializations every single time. There wasn't that much like, yeah, there was like very little deviation. So it doesn't seem to matter that much,
See, so
at least in the settings we looked at.
750, this times that is pretty vast.
Yeah, I think so. I think this is an interesting way to think about evaluation, which is like, maybe this will make some of the statistical people a little mad, but it's like everything is like a learned estimate of what your policy performance is, as opposed to like some kind of statistical measure for that. But yeah.
Is it like one MLP doing all the 3, or is it 3 different MLPs?
These are 3 different MLPs.
So in this evaluation, these are 4, let's say in the Open VLA one, these are 4 different Open VLA versions, I'm guessing.
Each one of these are evaluations. So okay, it's a little misleading. This is evaluations from the Open VLA paper.
Okay.
This is evaluations from the
I see.
Hamster
What are the
paper.
models then?
So the models are whatever the baselines are in those papers. So like this one might be Open VLA, this might be like RT2, this might be like whatever, like an MLP policy or like a CNN policy. It was whatever like in the Open VLA paper that they actually did their evaluations on. So that's what it was for this. For Hamster, it was like a mix of like Open VLA, RT2, and like other kinds of like 3D VLA policies. For Meta World, it was a bunch of like different CNN based and transformer based policies that I manually built myself to like manufacture good policies, bad policies, and stuff like that. So we could do more extensive testing on different variations across these. Yeah, so we're actually like agnostic to what kind of policies and methods that we use. We abstracted the problem away from what policies are actually being run.
But I'm guessing like since all of these are like, let's say Open VLA, when it's
Mhm.
evaluating on their benchmark, they might have, let's say, took RT2 fine tuned on your Open VLA, whatever the data set they
Mhm.
use. And evaluated it again. So I'm guessing if there is any bias created because of that, since all of the policies have been fine tuned on the same data,
I see.
would you say that, do you think that
Um,
creates this problem?
or creates what problems?
Like basically your, the conclusions that we are drawing, sort of right now, at least looks like biased because all of these policies are trained on the same data set.
Yes, we're not looking at generalization, I would say. Like we're looking at like starting from like no assumption at all. It doesn't matter what policies are actually running at the end of the day, what they were trained on. We're currently looking at like if we have access to the training data sets for each different policy, can we actually like do better evaluations, like make this process a lot more efficient? We don't have to think about that cold start problem. But for this, we like start purely from scratch. Yeah. Does that answer the question? Or
Maybe I'll follow up.
okay, okay.
I have another question about this. So like, I guess one thing that's nice about like if you use more like classical statistical methods is like you have some sort of like confidence bound given like some number of samples.
Yeah,
For
yeah.
something like this, like what do you see as like a way to extend this in the future so you can do that if you can't, get the ground truth?
You can. So like so we took we were very high level about this in the paper and especially in this presentation, but we took this there's a lot of work on like convergence for Bayesian active learning methods for how we actually estimate different probabilistic models. So there is a proof out there for doing this. I just didn't do it in this paper.
I see.
But like you have to, yeah, it's slightly different since we're using a learned surrogate model as opposed to like a probabilistic model that
Right.
estimates like based on a lot of these inputs. So it becomes a little more murky because you're not assuming that it's like a Bayesian like model with Gaussian priors that's actually trying to estimate these inputs. But now it's like a neural network, so a lot of the proofs start to like fall apart, right?
I guess that's
Yeah.
what I'm kind of getting at. Is
Yeah,
like
yeah.
trade-off we made. With,
Yeah,
like,
that is
this
the
more
trade-off we
positive-
made. We got like richer like understanding of like task representations and language representations, which I did try like using like Bayesian, like different kinds of Bayesian approaches. Like let's use a Gaussian prior. Like one of the advisors for this project, Willie, is he's like a Bayesian active learning guy. Like he only thinks about like the formal methods approaches, like the formal approaches to like finding like convergence bounds for these. And like none of those worked for the first like 4 months I was working on this project, which is why we switched over to this like approach. Because it's hard to actually learn from like generalizable language, like task information from language. From one-hot embeddings, it's actually reasonable to estimate what kind of policies, like what the performance of your policies are going to be, but you can't leverage the fact that there's shared information between all the different tasks that you have. Yeah, so it was a trade-off. Yeah, so a lot of these results are very empirical. Cool. So I think the first question is like, I talked about like what that policy representation looks like, but for the task representation, like we have like we come up with a few different task representations. So we use an optimal embedding. So this is using the same thing that I was describing earlier with how we came up with the policy embedding, like an optimal policy embedding. We apply that to just like assume a one-hot embedding or assume like a one-hot embedding, and then we learn like tasks that perform well are in one region, tasks that perform poorly are in a different region. So let's like create that kind of embedding for tasks, and let's call that our optimal embedding. And then we can take a language instruction, an embedding of our language instruction. That's another way you can represent a task. One thing that we have found with certain types of tasks is language embeddings tend to overfit to like representing the actual noun rather than like the verb, and the verb tends to be the actual like harder part here. So we did a more naive like weighted sum between the language embedding and the verbs in the instruction. This is just an experiment that this is kind of interesting. And then we can do like purely random one-hot embeddings and just assume that there's no relationship between different tasks. And generally we find across, these are just a subset of the results I aggregated. So you can see that like, let me just point here, the optimal embeddings in this corner over here, and for hamster and for MetaWorld, tend to be like the highest in terms of like the separation for, this is for average log likelihood. So this is essentially like on the y-axis is the average log likelihood. So let's take all the evaluations that we did and see how well our probabilistic models actually fit to the data, to all the data that we have. And every single time we do a new query, we're adding to our like building better and better like estimates or distributional parameters over time. So we generally find that the log likelihood starts to increase the best for the optimal variations for our task representation, and then the different language representations tend to be like a little bit better. So the verb and the language tend to be like closer to the middle. You'll see this like sandwiching behavior, and then the random being the worst. So like this implies that there is like useful information in the task information in terms of how the language embeddings can help learn better priors for trying to estimate performance. So given that, we use this verb representation for the rest of the experiments that I'll be talking about. Yeah, so
what, why do you think in the OpenVLA, like it'll?
it's all very simple. Yeah, so we put this one here because OpenVLA's tasks were very this is an interesting insight, which is like in a lot of places, the tasks are all very similar to each other. So like whatever representation you use for like language or like verb or random, it doesn't actually mean like anything because like there's not much variation between all the tasks. When your tasks tend to be a lot more diverse, which Hamster does and MetaWorld does, like they're very vastly different tasks that they did their evaluations on, you actually start to see like bigger gaps overall. Um, these are only like three of the evaluations, but we had like a bunch more in the paper across different kinds of like artificial and real evaluations. And you see similar behaviors there too.
So what does the task being diverse mean?
So like a lot of the open VLA tasks are all just like pick this task, put that down there, pick this, put that down. So like the language embeddings don't actually provide that much information about the task information over just using a like a one-hot embedding, right? But then if you have more diverse tasks like a bunch of like open drawer tasks, but then also some pick tasks, but then some like stirring tasks and some other like more diverse tasks, those actually the differences between those tasks in like language space tend to be a lot more important than, and so one hot embeddings like actually like destroy information in that sense.
For the verb.
The verb representation is just a weighted sum where we take the verbs, like so if you have a task like pick up the blue coffee mug, you take like the pick up part of it, like we just like extract the word pick up, get the language embedding of that, and then we have the rest of the sentence like pick up the blue mug, and then we just like do a weighted combination of those two embeddings, like weighted sum.
How do you weight it?
It was just like a naive like 0.7 times 0.3, like 0.7 for the verb, like language embedding, and then 0.3 for the like the rest of the instruction. So you merge those together, and then there's like more of an emphasis on the verb itself. Is because for certain variations, like the verb like is more important. So like we actually found in a lot of cases where if you had a task like pick up the blue mug or like open the blue like lid or something, or like or no, yeah, like variations of these kinds of tasks, like they would say there's more similarity based on the object alone as opposed to like the actual verb that's being done, and that's where more meaningful like information actually exists.
So how cluttered is the environment? Because I would.
For Hamster,
Cluttered than I would expect a mountain.
for this, we were observation free. So like we weren't actually leveraging the observation of what the robot was seeing. We only leveraged the task information and the policy like embedding. So the clutter of the scene didn't actually matter for how we were structuring this problem.
So what is the input?
Oh, this is the input to our surrogate model. For the policy, it gets like the observation and everything. But
You're saying- So
but-
those are the bosses for your.
for the surrogate model, yeah. These are the average log likelihoods for the surrogate model.
I guess for these evaluations, since you're not using the same complexity, do you see that, like, let's say for a certain task in a benchmark, they have, let's say, more complex and simpler scenes. Do you see like a larger variance in the success rate or whatever metric you're using?
Yeah, so I think Hamster is the more interesting one for all of these, since OpenVLA and MetaWorld have like relatively simple tasks overall. Hamster has like a wide variety of tasks with task progress. Like some tasks are like four-step tasks, and some are like two-step, some are one-step. And like as the complexity of the problem goes, you actually, I think what's more what interesting results that we found is that for something like Hamster, because like we found that like it's generally better at finding that like middle like performance ground, like if it's like 0.7 in terms of like the success, like the task progress to finishing the goal, we can actually represent that a lot better. Like yeah, these like middle performances, I guess.
Like
Things that aren't
average
full
performance?
success. Yeah. I don't think it counts as average performance. It's like what I was talking about in terms of like performance is relatively bimodal. So like if, for example, like in a lot of tasks, like let's say you would find like what you're trying to represent is you have data points here where you're doing pretty poorly. And let's say this is like 100% success rate or 100% in terms of task progress, but your policy like very rarely goes there. Let's say it only did it once. And then like the rest is around like generally here, like around like 0.7. So like more complex tasks generally have more points along like this continuous distribution, but we can actually represent like a distribution that like captures all of this.
Oh, I see.
Over.
Interesting, just by like how basically uniformly distributed your
Yeah.
bimodal.
Yeah. So like as task complexity increases, I wonder if we need to do like more complex probabilistic models to actually model the performance distributions. Like that would be my first guess on what you would need to do as tasks get more complicated.
I see.
But generally, like for the other tasks, like for OpenVLA and MetaWorld, like the like a unimodal versus a bimodal distribution or like more complex probabilistic models don't really like move the needle that much. But as you go to more complex tasks, you need more complex probabilistic models to model the actual performance distribution overall.
Yeah. So have you tested whether this generalizes to new tasks that weren't in the training data set, but they can just embed semantically and feed in?
Yeah, so did we put this in the paper? We're working, one of my undergrads is working on this, but like you can create a formulation of this problem where you actually hold out an entire task or like some subset of tasks, and then you check how well your evaluations are on the unseen tasks overall. It works reasonably well, but like we aren't publishing it yet because like it's like basically just this approach, but just like a slightly different problem formulation, and that's not interesting enough. So we're trying to improve on that right now. So I guess this approach does actually work for those unseen tasks relatively well. You have a decent enough prior. There's a lot of interesting formulations of this. So like currently we're just trying to figure out what the best like how to like estimate that whole like performance distribution is. But the way you do sampling can change if your goal is to find, like, let's say you don't really care about your poor performing policies. You only care about sampling more and more until you find what the best policy is, right? Or what the worst performing task is. So like you can design, or we've been designing different acquisition functions for those as well. But for this, we're just looking at like estimating that overall performance distribution across all policy task pairs. But the version you just said is like, I don't care about like, I care about like things I haven't seen yet, but it does do a good job with that. So let's say you do evaluate every policy task pair for your current setting, like you estimate that full distribution, it does do a decent job on things you haven't seen yet.
So, I mean, an example of that might be, you hold out everything involving placing something, right? It starts with something in its hand and has to place it. And that was never seen in training, but just through the encoding of the word, the verb.
The verbs, yeah.
Could like, I don't know, have you seen?
I didn't do full, like we assumed like there are some picking tasks, but let's say there's like a new object, right?
Okay.
And like we found
so new noun. Okay.
New noun. Yeah,
Okay.
I didn't try new verbs.
Okay, so
new
verbs
nouns
would be
work better. Yeah, new verbs would be really cool. I think you do like, I think you'd need like bigger and better like models to try to estimate the performance of like verbs that you've never seen before. Or maybe like if we can do like longer horizon tasks, but currently it's like shorter.
Tried, because it might be feasible to have a bigger model, surrogate model, if you just pre-trained in simulation on a bunch of tasks, as opposed to, having it, and then thought about, okay, well, we're going to just evaluate or fine-tune in the real world on a few tasks that haven't been seen before.
Wait, what do you mean? Sorry.
So you could just in simulation take a whole bunch of tasks with a whole bunch of verbs and a whole bunch of and basically just pre-train it on all of this in the exact same way that you have done.
Yeah.
And then if you wanted to know for either a specific task in the training data set or even one outside of the training data set or a new verb, if it has seen enough previous things and it has been trained in simulation, like it's not going to be as accurate as a physical world evaluation, but it might be able to generalize.
Yeah, so that's something we think would be really cool. But the thing is, like, you don't actually have a good prior on, like, you need a really good policy representation to be able to do that more generally across different policies and tasks.
Yeah.
We've been looking at things like, what if we create like a ground truth, like offline data distribution, and can we like run every single policy on that and just see what your like offline, like your loss or your offline evaluations look like on that? Can we learn a representation that generally represents your policies through that evaluation? And then we can do what you're saying. But that's why we've been focusing a lot on future work on how do we represent our policies? Like, how do you represent different VLAs or different checkpoints that companies are going to come out with? Or if you're a company and you have like 20 checkpoints you're currently testing, can you represent those that are used in such a way that it's useful to run methods like this? So like, it's kind of like opening this like new problem of how to do things is how I think about it.
So, bro, this is Peter, if I can, online. So,
So very
I've
quick, the next thing
I've
is like how do we actually select different acquisition functions? So there's actually a few interesting ways to try to do sampling for policy task pairs. One is just like you sample a different policy task pair, like put eggplant in the pot and like we're going to run RT2 and then, or we're going to run different version or a different version. You sample these policy task pairs. But the other thing you can always do is you can just do full on like task sampling. So like let's say like realistically when you guys all do robot evals, you select a task and you run every single policy. You don't like switch from one policy task into another policy task pair. You don't, no one really does that. So the other alternative is we select the best task and we evaluate every policy on those tasks, right? And there's like a smaller switching cost like when you do that. So that's like those are the two alternatives. And then so, but for each one of these, we can come up with a few different sampling strategies. One of them is random sampling. So you select a policy task pair just randomly. That's your acquisition function overall. Another one is to use an expected information gain metric. I don't remember how to describe this anymore since it's been a while, but essentially it's what I described earlier, where you're computing the entropy between like how noisy the distributions that you've sampled are. And it's based on a lot of Bayesian active learning literature. And the other thing that we can come up with is just weigh it based on the cost that we have. So we can take the switching cost and we just do a multiplicative term on that switching cost based on the switching cost. Yeah, well, like weighed by some lambda so that we can like make sure that it's like all relatively like normalized. So these are the three different sampling strategies and the two different types of like sampling generally. And what we find, I'll focus on the version where you do policy task sampling. I've been regenerating these plots, so I'm sorry that they're a little ugly. I need to make them look nice for my thesis defense. But like essentially, like if we take the average across all the like data sets that I described before, you can see that like if you do cost-aware evaluation, so we have the L1 error on the y-axis in terms of how far away you are from the mean. And on the x-axis is the normalized cost of like actually running all those evaluations over time. So like importantly, I think the main thing to note is like if you ran every single policy evaluation that you have in your data set, this would be the overall like a 1 would be just running every single policy task combination until you're done with your data set, you build it out. So if you finish sooner, that means you did all those evaluations and came up with estimates like earlier, like before, like at a much lower cost. So the red line is when you use our cost-aware approach, you start to sample a lot better and your estimates for the L1 error are a lot better as you go down. The EIG-based approaches and the purely random sampling tend to be a lot worse and like take a lot more evaluations to do those to do like all the evaluations in your full data set. So yeah, we see that like this like cost-aware EIG metric is a lot better generally. Interestingly, for task sampling, the cost is normalized slightly differently than the one on the left. But interestingly, with the task-based sampling, it's actually like a little harder to find a difference in aggregate across all the data sets. In some data sets, it performs better. In some other data sets, like cost-aware EIG approaches actually perform worse. So like in aggregate, they actually just like balance out. I think overall, I don't want to go nitty gritty into like every single combination. So that's why I'm just showing it's an aggregate. Yeah, but those are the general results at the end of this. And I think like there's not enough time for me to talk about the last one since I mixed questions with the rest of the presentation, but that's a good thing, I think. Yeah. So any like last questions, I think we're going to come up on time soon. But since then, I guess like overall, I've been working on different ways to like I think I've been hinting at like the future work that I didn't throw in here, but it's like, can we like come up with generalization across all VLAs? Can we come up with ways to learn policy representations? Can we leverage observations into all of this as well? So those are like the three different angles that we've been currently looking at in terms of expanding this work, which you guys all asked questions about. So I'm glad. Yeah.
So I guess like after running all of these experiments, what do you think are still the biggest failure modes in the manipulation like tasks that you found? What do you think are the bottlenecks?
the bottlenecks. I think like I I abstracted everything away and like I didn't actually look at like the true difficulty of any given task, right? But you can imagine like more dexterous tasks tend to be a lot more difficult than just like relatively simple pick place tasks. And like that, like the degree of that difficulty actually matters for a lot of evaluations. And like we don't treat different kinds of tasks like that any differently from each other. And so I think like I think like for these like more complex tasks like I described here, I think there's a lot of work to make these like more efficient in terms of learning how to estimate these. Also, like some tests are a little more compositional, like these longer horizon tests tend to be like step by step, but then we don't actually like taking this like distributional approach, you don't actually learn the those representations very effectively. So like if you found that you do pick tasks really well, and then you do like place tasks or like opening drawer tasks really well, like it doesn't do a good job at estimating like open the drawer and put something into it. Like it doesn't do a good job at estimating that, even though like this like two-stage task tends to be like a linear combination of like the two separate individual tasks overall. Uh, so I think that would be an interesting thing to actually explore in the future. Yes. Go ahead.
Question, so you learn a surrogate model,
Mhm.
task and policy.
Yeah.
I think all of them are in a specific environment. And the
Mhm.
tasks are, for each task, might be evaluated on some variance or some different, position setting for the
Mhm.
task. So, do you think it's possible to learn surrogate model, even considering the environment variance?
Yeah, it's a lot harder actually, I think, to learn like that the observation, like the actual environment being like in the loop.
Yes.
Yeah, I'm worried about that like leading to worse sample efficiency, right? Yeah, because like yeah, your policy won't be as sample efficient. Like you want your evaluation estimates to actually be sample efficient in a way where like it actually helps you in doing these evaluations, right? When you have very noisy inputs, like when your inputs and priors into your surrogate model are very noisy, like your evaluations are purely random. And like that means like you're not getting anything out of using our surrogate model in the first place, right? So I think it becomes a more a bigger sample efficiency question when you include observations into this. But like someone said like leveraging like simulation, maybe. I think that's like a pretty good way to like get a good prior. I think like we've been thinking about like mixing simulation data with real data for learning better surrogate models, given the policies that we know we're going to be evaluating anyways. I think that's like one good way to like have like decent surrogate models, avoid the cold start problem generally. But then like our approach doesn't take into account the sim to real gap at all, right? So like there's a lot of work to be done there. Yeah. Cool.
Thank you.